5.6 substitution rule, video part 2. I want to start with this problem where we want to do use substitution, but there's probably more than one way we can deal with this. Now I see a chain rule obviously in here, but how does that happen? If I take u being just the x plus 4, I have another x in the equation. If I take the derivative of x plus 4, it should be 1. So I have some more to deal with then. So I'm going to do this in two methods. So we're going to do method 1. We're going to let u be x plus 4. And in order to get rid of that x in the numerator, I'm going to go ahead and say I'm going to take this u equals x plus 4 and subtract the 4 from both sides and get x equals u minus 4. So I'm going to use both of these equations to do my substitution. Now I do have to take the derivative yet, so I have du, and then if I take the du of the first equation, the derivative of x plus 4 is 1, and I'm going to multiply both sides by the dx. So I have du equals dx. So I'm going to have to use all three of these equations to do my substitution. So when I go and do my substitution, I have du for the dx. I have the cube root of u. And then for the numerator, I'm replacing x with u minus 4. So now I can try and deal with this one. And what I'm going to do is I'm going to separate this into two different parts of my equation here. Oops, cube root of u. And then this will be du. From here, I can try to go ahead and simplify each equation. And the first thing I'm going to do is rationalize each denominator. I'm going to multiply this one by the cube root of u squared over the cube root of u squared. Remember, the whole goal is to have u to the third power as the radicand. So I'm going to do the same thing with this one and multiply by that same equation. And if I do that, I now have u, the cube root of u squared, over u, minus 4, the cube root of u squared, over u. And then from here, I can definitely go ahead and simplify this, du. All right, so from here, let's keep going. This is going to be u, so I'm just dealing with, and I'm going to put the radical in exponential form, u to the 2/3 minus, notice, well, wait a minute. Maybe I messed up on this second term here. Did I need to do that? So what if I want to say, okay, I went too far. I have to think to myself, maybe I didn't need to do it to both terms. I don't have to do it to both terms. So going back to my term back up here, I'm going to say it's 4, and then it's really over, and I'm going to put an exponential form, u to the 1/3, and then I'm going to go ahead and bring that up to the numerator and say it's 4u to the negative 1/3. Now, I have a situation that is much easier to go ahead and integrate. So I'm going to go ahead and take the antiderivative of each of these functions. I'm going to add 1 to the exponent and get 5/3. I'm going to divide by the new exponent, and I have the reciprocal here. The next one, I have 4 minus 4, u adding 1 to the exponent and dividing by the new exponent, multiplying by its reciprocal. I get this plus c. Now I can go ahead and neaten up and do my resubstitution, and I have for my resubstitution 3/5 x plus 4 to the 5/3 minus 6 times x plus 4 to the 2/3 plus c. Now, some people may leave it as this. And we may say, oh, it's okay. But truly, we can manipulate this further. And it's important to remember how to manipulate it further so that on a test, if it's multiple choice, you don't want to pick, no solution or none of the above. This could be manipulated into something else. So I'm going to do this once, and then I'm going to show you the other method. For what I'm going to do here is I'm going to pull out a GCF of x to the 4th to the 2/3. That's the smallest amount I can do GCF for the two terms. So I'm going to have x plus 4 to the 2/3 times, and then you see I'm going to have 3/5. And if I subtract that 2/3 from 5/3, I get 3/3, or x plus 4 to the first. That's the first term, pulling that out, GCF. The second term is just going to be -6 plus my c. All right, then from here, I can go ahead and I'm going to distribute this. I'm just going to neaten these big parentheses up here. I'm going to have x plus 4 to the 2/3 times 3/5 x plus 12/5 minus 6. But I want to try to simplify these fractions. I'm going to go ahead and put that this is really -18/5 plus c. Notice my goal is to keep simplifying this equation. Now, notice I also have it down to multiplication of two factors. And I'll have 3/5 x. And this should end up being minus 6. What do I do? 3/12 minus 6. Uh-oh. Sorry. All right, I know what I did here. This isn't 18. I was getting ahead of myself here. This should be 3/5, and then this should be minus 18/5. Now that makes much more sense. The plus c. All right, from here, keep going. I'm going to go ahead and factor out a 3/5 from this second parentheses and get x minus 6 plus c. So the only thing is, this is a little bit of a messy way of writing it. So my last step is just to write it in an easier way of reading it. So it's 3/5 times x minus 6 times the quantity of x plus 4 raised to the 2/3 plus c. And that is how you may see this in some other capacity. So yes, we had some kind of binomial plus c, but now we've got it all down to technically one term plus c. I'm going to show you now method 2 for the same problem. So remember, we went and we did the substitution of just the x plus 4 being the u. So if I'm given this equation again, and I want to do my u substitution, maybe I want to do the whole radical in the denominator. And if that's the case, I need to kind of undo the x. So I'm going to cube both sides of this equation, and then I'm going to subtract 4 from both sides of the equation. And then I'm going to be able to substitute this equation in for x, and then I need to take the derivative of this equation. So I'm going to end up having 3u squared du is equal to dx. So I took the derivative of this equation of both sides, and because of the chain rule, I'm sorry, not the chain rule, I'm sorry, the implicit differentiation of this equation, I had to multiply it by du dx, and then from here, I went ahead and multiplied both sides by dx. Now I can go ahead and do my substitution. So my integral is now going to be I have for u the whole denominator. In the numerator, I'm going to substitute in for x the u cubed, minus 4. And for the dx, I'm substituting in the 3u squared du. So I've done all this substitution. I've done this piece as my denominator with this equation. This is going to be substituted with this equation. And this is going to be substituted with this equation. And that's what I've done. I've substituted everything correctly from the first given integral. And now I've done the substitution. Now I need to go ahead and simplify, neaten up what I can, and take the antiderivative. So from here, I have a constant of 3 that I'm going to go ahead and bring out as a coefficient. I'm going to go ahead and make sure this is written as 2 separate, like this. Maybe you could have done it differently if you wanted to. You know you can do things more than one way. From here, I could see that I've got simplifying u squared minus 4 over u times u squared du. From here, now I'm going to distribute that u squared in, and I've got u to the 4th minus 4u du. Oops, lost that one there. Now, this becomes very easy to take the antiderivative of. Uh-oh. Squared plus c. From here, if I go ahead and resubstitute back in, I'm going to end up with the exact same equation that I did from there. So it becomes just simplifying again. And if you can see, maybe I'll take this one step further. I'm going to distribute that 3 in. Oops. 2 times 3 is going to be 6. And from here, when I go to resubstitute what I had in for u, and if I put things in exponential form, and we can see we're back to where we were in the previous slide. Then you would do all the same process of simplifying this into another form. Moving on, I want to go ahead and talk about what if we have the integral of tangent x, and what do we do with that? How do we know any antiderivative or any derivative of some function that had the answer being tangent x? How can I go and take the antiderivative? So this becomes, well, wait a minute. We're going to have to remember some trigonometry. So for example, we do know we can go ahead and replace tangent x with sine x over cosine x dx. And now I can do u substitution. So I'm going to let u be equal to cosine x. And taking the derivative, I get negative sine x dx. So I'm going to go ahead and do my substitution. I'm going to have for cosine x, I'm plugging in u. And if I go ahead and try to just plug in for du, the negative sine x dx, my only issue I have here is that negative. So if I divide both sides by a negative, it's a negative du that I'm plugging in. So from here, that negative is really a -1 that I can pull out as a factor. And then I have du over u. And then we can see it's really negative of natural log of the absolute value of u plus c. Going ahead and resubstituting in, I get the natural log, negative of the natural log of cosine x plus c. So from here, we can actually then take the antiderivative tan x. using u substitution, but we're going to have to use trig rules. And then we also know that we have to remember another thing about logs. If we have the negative natural log of a, it's the same thing as the exponential rule, bringing that negative 1 up as an exponent of a, and we end up having the natural log of 1 over a. So if this is the case, if I use this to correct this negative, and I bring that up as an exponent for cosine x, it's now really going to be the natural log of secant x plus c. So here's the thing. The book gives us a list of these trigonometric integrals, and you can memorize them if you wanted to, but the problem is you don't have to memorize these. You can use u substitution and knowing your identity substitutions from trig. So we're going to go ahead, and I'm moving on. We want to do substitution rules for definite integrals. And for this one, the only thing I want to do for this example is when we're given a definite integral, we have upper and lower bounds. So we're going to do u substitution, and there is two ways to go about this. One, you could take the u substitution, find the antiderivative, and then once you plug back in your u for x, use the correct bounds. But then your notation will not have the bounds in it. But for what they said here in the box, is they're changing the bounds with the u substitution. So we're going to go ahead, and this saves us from resubbing back in our u. So what I'm going to do for here is I'm going to say let u equal 4 minus x squared, and taking the derivative of it, I get negative 2x dx. I have a 2x in my integral. That's good. The only thing I have missing would be the negative. So I'm going to go ahead and multiply both sides by a negative 1, and now I'm going to do my substitution. I have for 4 minus x squared is going to be u, and then for the 2x dx is going to be a negative du. I'll get back to that negative in a second. In order to save myself from resubstitution, I'm going to find the new bounds. I'm going to evaluate u at my lower bound, which would be 4 minus 0, or it's 4. And I'm going to evaluate u at my upper bound, which is 1. And when I plug in my 1 into my u, I get a value of 3. So technically in here, my lower bound is 4 and my upper bound is 3. So I've got two things to deal with here. If I bring out this negative, I get this equation. Easy to integrate. The only issue is my bounds are not in the proper form. I'm going to go ahead and have to switch my bounds, which means I have to take a negative of this negative integral, and then I can go ahead and switch my bounds. So it really is saying it's now a positive 3 to 4 u du. And then because I changed the bounds, I can take the antiderivative of this equation, which would be u squared divided by 2, and we're going to evaluate it from 3 to 4. And then because I did the change of bounds, I'm going right into the fundamental theorem of calculus part 2 and evaluating. I'm plugging in my upper bound, and I get 8, and I'm going to plug in my lower bound and get 9 halves. And when I simplify this equation, I get 7 halves as my answer. I want to go ahead and do one more equation, and we're talking about number 67, and it has to deal with remembering trig identities. We have cosine squared of x dx, And we do not know any antiderivatives for cosine squared in dealing with a composite function. I'm going to have to do u substitution for this one. But if I did that, I don't know if I'd work out with the same answer. But there's got to be an easier way. If we can remember that we have identities for cosine squared theta, you can replace it with 1 plus cosine 2 theta over 2. And if we had sine squared theta, we can replace it with 1 minus cosine 2x. Or I'm sorry, let's do theta. Let's keep with theta over 2. You could use these to substitute in for the cosine squared x dx, and then you can take the antiderivative easily because technically this is 1/2 here plus cosine 2 theta over 2, and you can integrate that easily. And then cosine 2 theta, we know is just going to have that basically the anti of the chain rule. We don't even have to walk through the u substitution if we can remember that. So for this problem, I'm going to go ahead and replace this cosine squared with 1 plus cosine 2x, and I'm splitting this equation into 1/2 plus this over 2 dx. And then from here, taking the antiderivative of this first term should be 1/2 times x plus, I'm going to do sine 2x, and then I have over 2, and then I'm going to be multiplying by the chain rule, which would be by 2. And we're going to evaluate this from negative pi to pi. So I'm going to go ahead doing FTC with this one, and we see it's going to be pi over 2 plus, and if I plug in pi into sine 2x, it's 0. And if I plug in the lower bound, negative pi over 2 plus, and if I plug in negative pi into sine 2x, I get 0. And I end up with pi over 2 plus pi over 2, which equals pi.